Hi, my name is Leandro Facchinetti, and let's write some code together, shall we? What we have on the menu today is the second part of me implementing the RBJ filters. They are a very simple EQ in this library that I'm developing to produce JSFX. They are real-time audio processors in REAPER. So I'm developing this library that will help you develop better looking, easier to develop, more interactive JSFX. And many effects are going to need some sort of EQ or filtering of some kind, and RBJ's filters are probably the most popular one. They are relatively straightforward to implement, and we are halfway there. Let's implement the other half. So I found, when I was looking into this to implement this, and I found all these different sources for the same document, right? All these different sources. And when I actually started implementing, I think I used this version. And I said that I would, and I did, compare this version to all the other versions floating around. Now, you know what I discovered? That this is the outlier, that this is the one that is different. And it seems like it's the one that is out of date. There are minor tweaks, not in the sense that any of the formulas is wrong and there is no typos or nothing like that, but there are some simplifications that were made to the treatment of these coefficients with alpha and beta. So some of the things we wrote is wrong, and we are not even done with the implementation. So there is still a lot of work for us to do. So I suppose probably that the canonical version at this point is this one from musicdsp.org. I say that because many other places link to this. For instance, I think that this links to that. No. But this one, I think, links to that. You know what? I'm not even going to pretend that I understand the history of this document. It has been floating around for so long. Oh, see? This one is linking to that version. Bo is here. Hey, Bo. Yeah, it's you again. It's me again. We are doing this. So, musicdsp.org. Many other sources link to this. I suppose that this is the best version. And what I found by comparing all the, 6 versions of this document is that the versions that have been prettified, the versions that in which the mathematics looks prettier, I found that they were harder to read. Some of the spacing was weird and the indentation was misleading. For instance, there is some comment here about an intermediate variable that is handy. Yeah. So for instance here, the relationship between the shelf slope and this is that, and then this looks attached to this, right? But no, it's actually attached to that. And so this formula is related to this sentence here. So I find that when people try to format things to make them prettier, they actually don't make justice to the original document. And yeah, this version here is also out of date because it's referring to beta. So let's get rid of this old version. And maybe this version is the same one as in the DSP website, the Music DSP website. Just to be sure, I'm going to go to what I think is the canonical source, and let's download this file. And I am going to open this here. And in fact, I think what I'm going to do is, I think I'm going to put this link first. Right, that's that link. So this one comes first, and I'm going to leave for last these ones that seem out of date. So I guess this is my main reference. This is from all the formatted versions. This is, I think, the one I like the most. And I'm fairly confident that this TXT file is the same as the one I just downloaded. So let's put this on the same folder and then we can compare this. It is confusing, I know. So if I try to save this, it will complain. I need to give it another name. So I'm pretty confident this document is the same as this one over here. In any case, now we have both of them and we can compare. So let me open an instance of Visual Studio Code. Let's beat this down to death. Let's select this for compare. This is the version at Music DSP. This is the version on the other website. It is the same document. So two of the sources that I liked the most seem to agree that this is the best version. That's the version we are going to use moving forward. And that's the version that I linked first. And then this version I didn't really like. And this was an example of the misleading typesetting that I was talking about. So yeah. In fact, I think I'm going to take notes. Probably the canonical version. Typeset versions may be misleading. Plain text versions are better. I think that the plain text versions are better. And then more copies of the canonical version. And finally, outdated version. There you go. Bo is asking if we can talk about frequency and time domain some more. Of course, that's what we do here. We talk about time, we talk about frequencies. That's what we do here. Yes, if you have questions, ask away. If you have comments, you may comment. Okay, so this is the version that we are actually using, which is actually good that I ended up preferring the plain text version, because some of these I can just copy and paste, and I can open it in Visual Studio Code side by side with my formula, or maybe not side by side, but maybe like this. There you go. Oh, and I'm going to put my implementation on top, because sometimes I forget that I am in front of the text editor. So there you go. Now, let's talk about everything that we need to do here. So this normalization stuff we need to remember for later. Then, so I guess these names are different in this version of the document. But maybe I will keep the old names. Yeah, I think I'm going to keep the old names. For instance, in the old document, it was called frequency instead of F0, and I think I prefer to call it frequency. So I'm sticking to this document as much as possible, but not exactly. Maybe I will leave a comment like F0. And then dB gain we are keeping. Q, the bandwidth. Well, the bandwidth is in the document, it's called BW. And let's see. So big A, in the document that's called A. W0, I guess we can call this W0 in the document. Well, there will be the coefficients, they will be called A's. So this big A is misleading. But the omega thing doesn't tell me much. And over here, it's a W to look like an omega. So I guess I can rename this to W0. I don't know. I don't know what I'm going to do with these names. Let's talk about frequency and time domain. Bo says that he's a bit confused. At what point does the frequency domain start to be a time domain? They are different ways of looking at the same thing. If you have an audio signal, you have a chunk of samples. They are said to be in the time domain because usually it's samples captured over time. Now, that's just usually the case. It's not always the case. You may have like an array of microphones and you capture one moment in time. That may be relevant, for instance, if your array of microphones is trying to capture an earthquake. You may get a measurement of all the microphones at a certain point in time, so your time domain really is space. Never mind that. You have a block of samples, that's your time domain. Then that's one way of looking at that information. There is another way of looking at the same information. It's a lossless transformation. You're just looking at the same data in a different way. And that's the frequency domain. So you can do a Fourier transform to go to the frequency domain, and it's a different way of looking at the same data. An analogy I think I can make is we did something like this. When we were streaming together, we talked about mid-side. So you have a stereo signal, it's 2 channels, left and right, but you can represent exactly the same information, use mid, which is the commonalities between left and right, and side, which is what's different between left and right. But if you encode the signal using left and right, or if you encode the signal using mid-side, it's exactly the same information, and at the end of the day, you can convert from one to the other losslessly, and it's just a different way of looking at the same data. Well, that's the same story. I'm not saying that time domain and frequency domain have anything to do with mid-side. I'm just saying that it's the same principle. Time domain is one way of looking at block of samples, frequency domain, another way of looking at the samples. It's just a different representation for the same data. Does that help? Let me know. Okay, so where are we? In terms of the types and everything, I think I'm gonna go with my names. I think I prefer my names. Yeah, I have to decide if I'm gonna use my names or their names. I think I'm gonna use my names. So let's go to these types and annotate. Yeah, Bo, this is the kind of thing that you get and then you forget or you misunderstand and then you have to think about it again and then you have to maybe ask again. It's completely fine. But one thing that may help is that in the near future, we are going to implement a Fourier transform. And that's cool. I'm going to implement the Fourier transform mostly for fun because JSFX come with FFT already and it's probably faster than whatever I can implement. But we're going to implement it anyway because I want to learn how it works. So we're going to implement it from scratch and it will be part of the library, though I don't think that most people will use it because REAPER already comes with that. In any case, we will take an in-depth look at how the transformation works and we are going to see how to use it. Like, I guess the canonical example is we are going to build a spectrum analyzer from scratch. That's what we are going to do at the end of the day. So the plan is that I'm going to implement the definition of a discrete Fourier transform. Then I'm going to implement a fast Fourier transform. It will be a lot of fun, but not today. Today we are doing filters. So this in the document is called a high-pass filter, and this is a band-pass filter, BPF. This is also a BPF. This is a notch. This is APF. This is called peaking EQ, and I have no idea why there is this EQ suffix, because everything else is also part of a regular EQ. Low shelf, high shelf go by their usual names. Then I'm only putting the translation when I'm renaming something for the benefit of like readability. Maybe someday my version will be the canonical version because it's even executable, which is a nice property. And my version hopefully will not have these kinds of typos. We'll see. So Let's go to the parameters. The frequency is F0. dB gain is pretty straightforward. I guess I'm going to comment what are the types. Well, I already have an enumeration for the types, so suppose that will make sense. Then I have the type and the value, and then I have dB gain. And I think that now this is out of order, and I think I'm going to keep with my order though, because dB gain is only for peaking and shelving, while Q and bandwidth, they are for all kinds of filters. So this is like the exception. The dB gain is like the exception, only for shelving filters. So I'm going to keep the order of frequency, wideness, and dB gain. Right. So in terms of the dB, of the wideness types, we have Q, bandwidth, and S, which stands for slope. But Q is such a common name that before Bo said to me that it stood for quality, I didn't even know that. So I think I'm going to keep Q. But maybe S I will transform into shelf slope or slope. I may do that. Yeah, I think I'm gonna do that. Slope is my S. And the order here is different. And I think I actually prefer the order in this document. So I'll keep it as Q, bandwidth, and S. Why? Because in most EQs, you see a Q and not a bandwidth, except for REAQ. Whatever. Doesn't matter all that much. So these are like the settings, the inputs to the configuration of the filter. Then we have some intermediate variables. Oh, maybe I should have like configuration as a prefix. Yeah, I think I'm gonna do that. RBJ filter. Let's see what it looks like. Yeah, struct, RBJ filter, configuration, type, configuration, frequency, configuration, wideness, type and value, and configuration dB gain. And then we already have a method, which is not fully implemented, but yeah, it's here, configure. So there you go. And I remember already when I was looking at the code after the stream finished that I forgot to put the RBJ filter as a parameter. So over here, I'm using the RBJ filter all over this function, but I forgot to pass it as, or to include it as a parameter. And the sad thing about doing this, about forgetting this parameter, is that in JSFX, every variable just starts existing as soon as you start using it. So RBJ filter would just be 0, which is the wrong address. It would be a mess. All right, so coming back, we have our configuration, and then we have our, I guess I'm going to call this the intermediate variable. And then I have my big A. I have my... Oh, so check this out. Now that I have this intermediate variable prefix, I could just call this A and it would be different. But I guess I won't. I want to keep things straight. Now for omega, I'm going to call this W0 because I know what omega is, but I don't really care all that much. Not enough to call it omega. No, I think I'm going to call it omega. I'll tell you what omega is in this formula. Omega is, you take the frequency that you care about, you divide by the sampling frequency. That is a proportion. So if in the frequency spectrum you have 48, if you're sampling, GEC says, hello GEC, great to have you here. We are talking about Omega, what this guy is in these weird equations that we are using for the filter. Well, so you start with the frequency that you care about. This may be like the cutoff frequency of a low-pass filter, for instance. Now, the first thing you want to do to that frequency, it may be something like 2 kilohertz. Okay, so let's say that this is 2 kilohertz. Then let's say that your sampling frequency is, or sampling rate, your sampling rate is 48 kilohertz. Then what you're interested in these formulas is what is the proportion? Am I at 0.3 or 0.4 of the sampling rate? It's a proportion. And because of the Nyquist theorem, the Shannon theorem, this F0 can only go up to 0.5, right? So the frequencies go from 0, the so-called DC or direct current, up to Nyquist, which is 0.5 of the sampling frequency. So for instance, if F0 is 24 kilohertz, then this would be 48 kilohertz, this would be 0.5. Okay, so that is just a proportion. It is a way of representing a frequency that is independent of the sampling frequency, because if you go to 98 or to 96 kilohertz, then the proportion is going to be the same, right? You just, in that case, I guess you would take this frequency and, or the proportion is not going to be the same because this number has increased, but you're still going to represent the frequencies that you can work with from 0 to 0.5, half of the sampling rate. Okay, so that is just the proportion, but what is this 2 pi doing? Well, 2 pi is the length of a sine wave. So if you have a sine wave, the length of a full excursion going up and down and then back to the beginning, that takes 2 pi. In other words, that's the length of the cycle of a sine wave. So what we are doing here with W0 or omega is we are computing the proportion of the length of a sine wave. Or in other words, we are making a length, we are calculating a number that could be a length for a sine wave of a certain frequency. That's what this W0 is about. And then it comes up again and again, almost everywhere in all the equations we are going to need. Okay, that was a fun exercise, but it's not really important for the implementation. It's just more for understanding the mathematics a little bit. We are understanding it bit by bit as we go. GEC asks, can we make a JSFX transpiler in Go or some other language so I don't have to learn a new one? Of course. Yes, in fact, there is already a project related to that. Let me see if I can find this. It is not exactly what you want. Yeah, so there is this package that is a language that extends JSFX. So you will still have to learn JSFX to use this language, but it gives you more infrastructure. It gives you more facilities that don't exist in JSFX proper. For one thing, it gives you enums. Now, there are many interesting things about this. First, I implemented enums as well. So what gives? Why am I using a different mechanism? I'm doing it in the language. I'm trying to avoid this notion of compiling to JSFX as much as possible. I'm trying to do most things in the language itself. Now, there are some trade-offs. The good side of things is that with my implementation, because it's in the language, it's just JSFX. You don't have to use a preprocessor. You don't have to install Node.js. You don't have to understand things in Node.js. You don't have to, every time you want to test your plugin, recompile. So you can just save a file in the REAPER IDE and immediately it will pick it up and it will start running your effect, which is great. So that's an advantage of doing everything in the language. The disadvantage is the expressiveness. I have to be a bit verbose, for instance, when I'm declaring my enumerations. I have to do things like this, which is kind of awkward. And if I had a language that I could invent some syntax, I could sweeten that up. Syntax sugar. So the choice of Geraint, who created this library, was to create another language that would compile to JSFX. But he decided to extend JSFX, so it's just new functions, new syntax constructs on top of the existing language. It's a superset of the language. Now, what you were describing is a transpiler in another language. So maybe you would like to write your JSFX in a syntax that looks like Lua or Go or JavaScript, and that would compile to JSFX. Is that possible? Absolutely. Has it been done? I don't think so. Is it a valuable exercise? I don't think so, because I really like being able to go in REAPER and edit, not this instance, this is me speaking. I really like being able to go in REAPER and change something and reload and everything is just running. I think it's super valuable to also have this on the right. And as soon as you introduce this transpiler in the middle, you either have to have some sort of mapping back to the source so that the variable names that would be generated make sense. And that's something called a source map. Or you lose some of these niceties. You are not able to debug as easily. And ultimately, you have to learn a new language. And I find that most commonly what happens is when you come up with these other languages that compile to a language, you end up having to learn the base language to begin with, like to be able to read the documentation at the REAPER website for JSFX. I mean, you still have to learn about the language, right? Because you need to know the limitations of what you can and cannot do. Some things are fixable with syntax or a library, like, for instance, enumerations is something that we can come up with. Though it does not exist in JSFX, we can create enumerations. But there are some things that are intrinsic to what JSFX can do. There are some features that you just simply cannot implement. So you still have to learn about JSFX to learn what are the math functions that comes with JSFX and that sort of thing. So all the examples here will be in JSFX, for instance, this part. And if you don't know how to read the language, then you wouldn't be able to read this documentation. But if you read the documentation, then you know the language. So what is the value in this preprocessor? I mean, I still see some value. And I still see value, for instance, in the library that I showed you, the preprocessor that I showed you. But I decided to try to avoid that as much as possible. If we hit a wall and having a transpiler is the only solution, we'll do it. And yeah, I spent 6 years in graduate school thinking about all these issues. I was doing a PhD in programming language theory, so I can speak about this the rest of the stream. But let's not. So yeah, I was here at Omega, and in the literature, it's usually called Omega. It's not called W0, so that's why I'm calling it Omega. And then we have sine and cosine, but that's actually misleading, right? Because what it actually is omega sine and cosine. It's the sine of omega and the cosine of omega. So that's why I'm going to call these guys these things. And this is how it's represented in the document. So I'm going to write it like that. Then we have here alpha and beta, but in this version of the document, there is only alpha. It has been consolidated. So I'm going to get rid of my beta. Did I already do that? Where is my beta? Oh no, yeah, it's right here. So I'm going to get rid of my beta here because I will be using these formulas. And remember how 2 days ago when I started this, I said that I remembered seeing some equation to relate queues with bandwidth. Here is the equation. It was not in that original version of the document. It is in this version 2 of the document. All right. So I think I have the names of my data structures, and maybe I would just, because I am naming parts of things like configuration, intermediate variable, I will have coefficients. And I'm going to be the first to say that this variable name is like super long and awkward to work with, but it's so expressive. And if you're trying to get your head around things, I think it helps to be explicit like this. And I am writing a library. I mean, this is not the first implementation of RBJ filters. This is not the first library to do many of the things that I'm doing in my library. So one of my goals in my library is to learn and to try to pave the way for people who are going to come after me. So I'm trying to make things as readable and as possible. And that's why I also do it on streams. And then our X and Y, I think, are so straightforward that I'm not going to name them. I think. That's my feeling anyway. So let's go over this one more time. We have our types with the corresponding annotations. We have our whiteness types, Q, bandwidth, and slope. Then we have the type, the frequency, the whiteness type and value. And I'm not sure I like this name, but I don't have a better idea for it. It's how wide the curve is usually. I don't know. GEC asks, so is this language EEL2 or JSONics? What is the actual name of JSFX language? Okay, so JSFX is this kind of, I keep opening the wrong Reaper instance. JSFX is an effect written in a language called EEL2. So EEL2 is the name of the language. JSFX is what you write in that language. And JSONic is the name of an old project that started this whole thing. That's why it's called JS. That's why it's called JS. It stands for JSONic effects, as in like audio effects. And it's called JSONic because this started like 20 years ago when Justin, the developer of Winamp and Reaper, was working with hardware for guitar pedals, and his pedal board looked like a cross. So JSONic and JSFX. EEL2 is the name of the language in which you write JSFX. And you also ask about slope. Slope is this type of whiteness that only makes sense for shelves, and it is how steep the shelf is going to be. So let me put another EQ here so I can show you what I mean. So if I have a high shelf, if I have a high shelf, there you go. This is going to determine how steep the shelf is, if it's very steep or if it's not steep at all. And there are different ways of defining this. One is Q, another is bandwidth, and finally, the third way is this slope parameter. And this document even explains a little bit what happens. So for instance, if the slope is 1, then it is as steep as it can be without overshooting, without doing this. So monotonically increasing or decreasing means that it's not going to overshoot like this. It's monotonically increasing if it goes like this, where it doesn't overshoot. It doesn't go up and then down again. Now, I wonder where we start to see the overshooting here. It's definitely before 1, so I think it's going to be at 707. I think that's going to be the relationship. And 707, I think it's 707, which is like the super important number. It's the square root of 2 divided by 2 or whatever, and that's when the Q is at a certain position that is special. In fact, I think if I make a new band, it's going to be like that. Okay, so it's the 707 has been rounded off to 7.1. There are some electrical engineering properties of this number. I don't know what they are. Whatever. Okay, so we have all the names. I like them now. I think I'm happy with all the names. So let's split this document, keep the names on the left. No, I don't have enough screens real estate to do this. Maybe let's split this document and put it below so we can refer to these names when necessary. Now, to create a new filter, that's a data structure, okay? So it's a data structure that is going to keep around your configuration and intermediate variables. And you can use this data structure. You can configure the data structure, and then you can call a function that we have not implemented yet. You can call this function that will do the filtering. We'll get there in the next 50 minutes. So this RBJ filter is the data structure that I'm going to return, and in this place, I'm just going to start all the variables. So let's refer back to them. I think that at this point, I changed so many things that it may be advisable for me to just replace all these lines. So yeah, I think that's what I'm gonna do. There you go. And I'm going to remove the beta, of course. So now let's review this. My configuration type will be just undefined. It's an enumeration. Yeah, it starts here. Type, and then frequency, and whiteness type, and value, blah, blah, blah. All that makes sense to be undefined when you create the data structure. Now for the A's and B's, I decided before to have only the 2 of the A's, but to make it match the equations better, I think I'm going to store all 3 of the A's. Yes, that's what I'm going to do. I'm going to store A0, even though I'm going to normalize everything else. So A0 is extra information. It's not really used, but I'm going to keep it around just for debugging purposes and to make the formulas look better. Then for, these names have changed, right? So I need to remember to do that. Whoops. And bam. Okay, so then we also have our X and Y, and I'm going to store 3 samples in them for the same reason why I'm storing 3 samples in A. I want not 3 samples, 3 coefficients. I want the thing to look better in the formulas that we are going to write later. And when I'm creating the coefficients, I don't know what the coefficients will be, so they are undefined. But when I create the circular buffers for the inputs and outputs, I want them to be 0 to begin with. I don't want them to be undefined. So that when you start cranking the filter, it will have just zeros in there, doing nothing. Good stuff. All right, so I think that the initialization is correct. And then for the configuration, I'm going to need the RBJ filter data structure that you want to configure, and then the type, the frequency, the whiteness type, the whiteness value, the dB gain. Nothing about this changed. Then for local variables, I'm going to compute big A omega, and I'm going to compute so check this out. The names here are already right. It's omega sin and omega cos for sine and cosine. And I have an extra comma at the end. And I'm also missing, so let me see. I have big A, omega, sin, cos, and alpha. I need my alpha there. And I think I may want to have variables here for, yeah, I think I'm going to do that. I will have A0, A1, A2, B0, B1, B2. Think that this is going to clear some parts of this code. We will see. So this is, again, the method that you call, or the function that you call to configure the filter. So to set all the configuration parameters. And I have this as an extra function. I could just have this in new, but I do this in this extra function because I want you to be able to create a filter and not necessarily know what kind of filtering you may want to do. Maybe you just have like, maybe you can just create all the filters in advance in the initialization block, but only when the user clicks on the user interface that you actually configure that and enable that filter. Yeah, that's why I have it this way. So let's see what we have here. The first is we are doing some error checking. Let me go over that again. So the situation is, if I have dB gain, it is only used for peaking and shelving filters. So dB gain needs to be undefined. In all other instances. So I'm checking. Am I on a peaking filter? If I'm not on a peaking filter, I'm not on a low shelf, and I'm not on a high shelf, and the dB gain is not undefined. In other words, I set a dB gain. The dB gain is defined, but I am on a low pass filter, for instance, right? Because it's different from peaking, it's different from low shelf, and it's different from high shelf, and the dB gain is not undefined. In other words, dB gain is set. That's a mistake. So I can error in that case. And I have a to-do here, which I think is stale at this point because alpha and beta, I don't even have a beta anymore. So I think it's fine. And then at this point, I am going to configure, I'm going to just set these configuration values, which are essentially just the stuff coming in, right? The type, the frequency, the whiteness type, the whiteness value, and the dB gain. So these are just the stuff coming in, the parameters coming in. I want to store them for debugging purposes. So I think I want to do that probably last. So I'm going to cut this code and I'm going to paste that at the bottom. And then I'm going to rename this as well because I now have this configuration in the middle of the name. Right, so type, frequency, whiteness value, whiteness type, whiteness value, and dB gain. Then I have to compute all of these intermediate variables. So let's go to the formula for them. So I already checked that all the parameters coming in, the configuration coming in it makes sense. So let's compute big A. Now, if I guess it's the same condition, isn't it? So let's have a local variable for that. Is peaking or shelving? That is equal to okay, so I am peaking or a shelving filter if my type is equal to this, or if my type is equal to that, or if my type is equal to the other thing. I think I want to style this and typeset it like this. So now I can check. Oh, I'm messing up the syntax here. Let me copy this line over there, and I'll just declare this variable over here. All right, so I have, am I peaking on shelving? So in other words, I can change this condition to be if I am not peaking or shelving, and yeah, so I think this reads nice. This sentence says dB gain only used for peaking or shelving filters. So if I am not a peaking or shelving and the dB gain is not undefined. Oh, but there is another error, isn't it? Isn't there? Well, I guess I could check for undefineds everywhere. Like I could check, do I have a dB gain if I am on a peaking or a shelving filter? But that becomes old, right? If I check for undefined everywhere, oh, it would be boring. I guess this is kind of an error case. It's even a sentence here. So I'll have an error check for that, but I'll not check undefines everywhere. I mean, there's only so much defensive programming that I want to do. So let's go back to the definition of big A. So if I am not is peaking or shelving, if I'm, okay, I guess I'll define it like this. Right? So if I am peaking or shelving, yeah, I'll do it like this. So if I am peaking or shelving, then this is the formula for big A. Otherwise, big A is undefined. I'm going to move some of these lines to the end. So we can focus on the computations of the formulas, and then later we can just store everything in the data structure. And this is particularly important because these values will be used, like big A will be used in other formulas below. So it's good to have a local variable for this. Now let's think about omega. Omega is 2 times pi times the frequency that came in. That's what we are calling F0, divided by the sampling rate. So that formula is correct. Then we have an intermediate computation of sine of omega and cosine of omega, and we are calling it omega sine and cosine. All right. And it starts with cosine, but I think I'm going to keep my order because I like it that way. Then I have here a computation of alpha, and I think I want to have it as a local variable. And this is going to change for the most part. Yeah, I think I'm just going to delete that and start over because this is something that changes from the old document I was using on Tuesday to this version of the document that I'm using now. So let's see. Alpha is, in case that I'm using Q. So in other words, if my whiteness type the whiteness type is one of the parameters coming in. So if my whiteness type is equal to Q, in that case, I'm going to use this formula. And we have a name for this computation. It's omega sin divided by 2 times the whiteness value. Just like that. Let's double check. So if my whiteness type is Q, if I am in this case, then it's omega sin divided by 2 times the Q, which is our whiteness value in that case. Otherwise, if my whiteness type is bandwidth then I'm going to use this formula instead. Oh, and there is something super important that I forgot to check here. So there is another error condition. Let's put parentheses here and check this other error condition. The other error condition is if you're trying to use if your whiteness type is slope, and you, well, I guess if your whiteness type is not, hang on, why do we use S? For what do we use S? For shelving EQ only. Okay, so maybe I'll have another variable here called is shelving. And maybe now these are short enough that I can put them in a single line. So one error condition is if I'm using the dB gain, but I think the dB gain comes later, right? Yes, the whiteness comes first. So let's check the whiteness situation first. Yeah, so let's check the whiteness situation. So if my whiteness type I'll be back. Okay, I just checked. The baby is alive. I think that he's going to continue being alive, at least for now. Okay, so let's check. We are working with the whiteness type now. And if our whiteness type is slope, well, I guess we are checking the... I got sidetracked. Let's try to focus again. I am checking the whiteness type. I'm trying to check the error condition in which you're providing me a slope, but you are not in shelving. So if you are not shelving and you try to provide me a slope, I'm going to error. Okay, now I think I nailed this. So S is for EQ on for shelving only. So if you are not shelving and you try to provide me with a slope, that's an error. And similarly, dB gain is only for peaking or shelving. So if you are not peaking or shelving and you try to provide me with a dB gain, error in that situation as well. Okay, that's some good error checking right there. Right, let's go back to our alpha. So our alpha, in case I am using a Q, it's omega sin divided by 2 times the whiteness value. If I am using bandwidth, I think there may be something that I want to rename. Yeah, I think that right before this type situation and this whiteness type situation, I want to have a configuration word. Yes, I will have that. So let me do this on this buffer on top so I'm not hiding what I'm doing. let's look for all occurrences of this, of that. Okay, I think I will be able to do this without much consequence. I'll just say configuration __. The reason why I'm doing this is so that now this matches that, right? L struct RBJ filter configuration type, and then the different types. And same for the whiteness types. Now, I should look in the rest of the project for RBJ filter __. Type, because I need to put some ___ configuration in there. And I need to look for my whiteness type, because I need to put maybe just whiteness, because there is whiteness type and value, doesn't matter. Yeah, just putting the configuration word in there. Okay, I think I nailed this renaming, but I'm renaming so many things so fast that it's hard to tell. Now this line became too long, so I'm going to break it into this other line I'm happy with. I don't care. Or maybe I'll break it as well just for symmetry. On Tuesday, I was talking about how I don't really care about the lack of syntax highlighting for EEL2 in Visual Studio Code, but I do care about the lack of automatic formatter. That's why, as I have to think about these things like symmetry and whatnot in the code. It's not good. Okay. And you may also be thinking, why do I go with such long and explicit names for these variables and I don't really care about the names of these ones? That's because they're local. They are either parameters to the functions or to the function, or they're local variables, but these other names are global. That's why I make them so explicit and long and obnoxious, I'll be the first to admit. Okay, so let's try this again. If my whiteness type is bandwidth, then I have to use this formula. Let's go ahead and code that formula. It is omega sin times the sine hyperbolic of log of 2 divided by 2 times the whiteness value times omega divided by omega sin. I think that's right. So let's go over this again. This is omega sin, this is this variable, then times this, the sine hyperbolic, the hyperbolic sign, was something that we implemented on the last episode. It's still lacking tests, and it's still missing some other things actually. It is missing the arc sine hyperbolic, arc cosine hyperbolic, so the inverse of sine and cosine and tangent and so forth. We'll do that, but not today probably. So let's continue. Sine hyperbolic, and then log. In JSFX, I think that log is base 2. Let's check that again. I think I checked that on the last stream, but I'll check it again. Yes, log is the natural logarithm. So log of 2 divided by 2 times the whiteness value times omega divided by omega sin. Alrighty. Next, if my whiteness type is not bandwidth but slope, Then I'm going to use a formula that is very similar to the one above. So I'm going to copy and paste that, but we're going to change it. So it's sine of omega divided by 2 times not the hyperbolic sign of anything, but the square root. In this document, it's using square root like this, and this is actually valid JSFX stuff. It's valid EL2, which is fun. So this thing in here will change, right? Yes, it will. So this is big A plus 1 divided by big A times 1 divided by the whiteness value minus 1 and plus 2. Don't you just love these formulas? It's crazy. Let's go over this again. Omega sine divided by 2 times the square root of big A plus 1 divided by big A multiplied by 1 divided by the S, which is our whiteness value because that's our configuration, minus 1 and plus 2. Okay, I think I got alpha. And I was thinking that maybe I would implement a function, an auxiliary function, just for your convenience, that would be the relationship between Q and bandwidth. Maybe you want to show both to the user for whatever reason, or maybe you want to have, yeah, probably for display. It's probably for why you would do this. So let's have a to-do below this whole thing. Equations, or maybe just Q to bandwidth. And the thing is just, it depends on the kind of filter. The relationship between Q and bandwidth depends on the kind of filter. So I guess it would be RBJ Q to bandwidth. And there is even an analog and a digital version of the same formula. Yeah, so maybe we'll do that. Then after computing alpha, so there is a relationship between bandwidth and Q, and a relationship between S and Q. Cool. Right. Let me save this, and then next, so here I have a fix me, allow for shelves with bandwidth. I think that has been fixed in this version of the document. This fix me was relevant in the old version of the document. Because now there are ways for you to define shelf with bandwidth because there is only one alpha, there is not a beta anymore. So there you go. And that means that this whole shenanigans to construct beta is just obsolete. Right. And then there is this handy intermediate variable for shelving EQ filters. Let's try to understand what this is about. Let's go to the computation for some shelving EQs. For instance, this. And I think I need to put this up top so that we can see without wrapping. So let's see where this is even relevant. Oh, it seems like this variable is used many times. But so is a plus 1 and a minus 1. So I guess I could have an intermediate variable, but we are not computing this often, and I think I want the formula to just look at as this as much as possible. So I'm not going to compute that intermediate variable. Finally, compute the coefficients for whatever filter you want, and that's what we are going to do. So let's start this by checking the type. And the type can be any one of those. So at this point, I can do that. And I can write, if my type is equal to that, then do a formula, which will be a block. And in this block, I will have to compute. Oh, the b's are given first. Go figure. So I'll have to compute b0 equals something, b1 equals something, b2 equals something, a0 equals an a1 and a2. And then I will have an otherwise situation. Like so. And then this last one will just be a semicolon. Next, I'm going to leave this as is, it's half done, and I'm going to take care of these sets at the end. I'm going to set all the parts of the data structure, and then I'm going to come back and copy over all the formulas, which will be like manual work. So over here, I have the definition of my data structure. All the configuration is already in place. So we just need to take care of our intermediate variables, as well as our coefficients. But I'm going to start with my intermediate variables that have already been used. So they are just there for debugging purposes. And you can see that I'm using Visual Studio Code like crazy to try to save myself some work, right? Multiple cursors to the rescue. There you go. But I also need to store my coefficients. So my coefficients are an array. So I'm going to maybe get a hold of this array. Yeah, I think I'm going to get a hold of this array. Yeah, I'm going to do that. So I'm going to have my A's and B's. And then I am going to L struct get from the RBJ filter the coefficients A. That is going to be my A's, and my B's are going to be my B's, like so. And then I have an array, and with an array I can use L array set on my A's at position 0, A0. Now, because the document is using B's first, I think I'm going to go ahead and use B's first as well. So let's see all the places where I'm using A, and I'm going to put it second. Not that it matters that much, but I think it's a nice thing. So on my B's, let's start with the B's. At 0, I will put B0, and so on. So maybe instead of calling it A's and B's, I can just call it A and B without an S, because I already have indices on all other things. So there you go. B and A. So that's another instance where I want to reorder things. And then I can set to that array at position 0, 1, and 2. Is that in that order? Yes, B0, B1, B2. Then repeat for A. And naturally get rid of the S over here. Okay, I think that is all the preliminary work to configure a filter. Now all we have to do is just copy over the formulas. Let's start. I think that they are in order. Low pass. Yeah, I was thinking about maybe just copying this and doing like a global search and replace for codes of W0, but I think I'm going to do it by hand to avoid typos and whatnot. Or maybe it causes more typos, who knows? 1 minus omega cos divided by 2, 1 minus omega cos. That's the same. And that is my low pass. Oh, that's similar, isn't it? I'm gonna start copying and pasting stuff because it is similar. Aria says, qual é? Qual é, Aria? Where do you get this? Do you go to like Brazilian slang websites? So Aria, this is gonna sound familiar to you. I'm doing something that you have done in the past, implementing the RBJ equations. You're saying that you hear some artifacts from my mic feed, possibly from the noiser REAPER. I did not change that. I didn't even change my limiter. I said I would, but I didn't have the time. So maybe you are hearing the denoiser that I was using before. I can mute it. Now it's no longer there. Does that help? Thanks for letting me know, by the way. So we are doing a high pass. That's the same as that one. 1 plus alpha minus 2 times omega cos 1 minus alpha. Arya says, oh yeah, I was looking at this last night and realizing how much I forgot the bit that I learned. Well, this is your second chance, my man. I am implementing this so that you don't have to do it. And here I have two options of equations I can use. Now, this version is using Q's, but I may be using a different whiteness type. So I'm going to use the equation on the left, which is omega sin divided by 2, 0 minus omega sin divided by 2, 1 plus alpha minus 2 times omega cosine and 1 minus alpha. That is going to be easy. I should have a song for when I'm doing this kind of thing. Maybe it could be song number 2 that we record on our Wednesday streams. Because I cannot speak and type this weird stuff at the same time. I'm not that guy. I mean, I'm just copying things over and my brain is melting. Because I'm having to translate these names and I'm having to translate the spacing that I like, and it's trivial stuff, but still messes with me. Okay, so far so good. I was checking that I was in the peaking one, and this is the peaking one, so I did not skip one by accident. And we are doing this. Okay, time for a break. What is up with the chat? Okay, yeah, gets rid of the artifacts, but there is noise now. Either way is fine, really. Either way is not fine. Noise is not cool. What if the profile was wrong? Now I was supposed to build a different noise profile, but the thing is so quiet that there is no noise. So I guess I'll have to turn off my gauge. And now there is a different noise profile. Maybe that helps, Arya. Let me know. Fun stuff. So, hello, Bo. Wait, can you use Reaper as an audio output for streams, etc.? Yes, you should watch one of the streams we did on Wednesdays. Arya and we talked about our streaming setup for 6 hours. It was my longest stream ever, but yes, Reaper can process audio in real time. And if you have the right pieces of gear on your computer, and by gear, I mean software, Blackhole basically in macOS and Virtual Cable in Windows, or I think. In any case, if you have the right pieces of of software, you can wire audio into Reaper and out of Reaper and into OBS. Then you can use Reaper to mix the audio, which gives you a lot more possibilities. So over here, I'm routing the audio in all different and weird ways for when I have guests over. I want to send them the audio of my voice and my computer, but I don't want to send them their own audio, so I have a mix minus going on. In any case, I have a lot of mixing weirdness going on here, and I do have audio effects that are processing all of this in real time, and I'm sending that to OBS and to the stream. So yes, it's something that you can do. It's super cool. Yeah, and there are people who use Reaper as an audio mixer for like live events with multiple microphones. And they use my auto mixer. It's a lot of fun. I rendered out some wave files for a project, and they didn't sync with another project. I don't think that this is related to the rest of the conversation. Yes, we all do, and check older streams where I spoke about. Yes, so yeah, it was a long stream, but it was a lot of fun. No idea what's happening, but you had syncing issues with my files. I think I got that sync working. It was a quarter note off. Good. You don't happen to remember the name of the stream? Okay, I think I can find that. If I go to Studio and Content. Oh, I think it was back when I was not naming the streams. I was numbering them. But it should be easy to find, because if I find a stream that is 6 hours long, then that is the stream. So let's talk about audio processing, title, content, stock, and then duration 6 hours. That is the guy. Copy the link, paste it here for your benefit. There you go. Weirdly, I tried to my render twice. Okay. There you go. Right, that helped. REAPER is very artifacty. You can also reduce the window size on REAPER, and that helps. Okay, I can do that. Let's go with 124. Does that help? I can also bring down this noise profile so that it's more subtle. And I guess I have to rebuild the noise profile from time to time because I change the room. And yeah, I think that different times of year may have different noise profiles. So yeah, let's continue this. I only have 2 more to do. I'm almost there, but these 2 are long. But that's okay because they're mostly the same thing. So let's do a low shelf. Okay, I'm going to double check this because I'm going to start copying and pasting this. So it's big A times big A plus 1 minus big A minus 1 times omega cos plus 2 times square root of big A times alpha. That is correct, it seems. So I'm going to copy this over, and I think I'm probably going to style this the same way that he styled on his document, because all the other ones are not aligned or anything. But this one, because the formulas are so similar, they are aligned, and I think I'm going to follow suit. So if I have a 2 times in the beginning, then I can have it like this. So I guess this is one advantage of not having an automatic code formatter. So I can do this sort of thing. So in this one, I just don't have the later term. And I'm going to put the parentheses like so. So it looks super nice like this one. And then this one is going to be similar to that one, except that this plus turns into a minus. And this is going to be just that. Oh, no. I have to be much more careful. These pluses and minuses, I'm getting all of them wrong. Oh man, this is so intricate. I'm happy that I'm writing this because then no one will ever have to write this again, right? Right. The next fellow is gonna come right after me and say, "Oh, but I want to learn all these things. Let me implement all of these again." Such a foolish endeavor. Oh, I forgot to format this one. Yeah, the RBJ filters have been implemented in JSFX for like probably 15 times. I could have just used one of them. But I think there is value to the way I'm doing this, and I haven't really touched on this yet. But why am I implementing things in the way that I am? Because unlike all the other implementations I found, this you can dynamically allocate, which well, it's not really true. You cannot dynamically allocate this while the effect is processing audio. You cannot be allocating more and more filters because the memory allocation needs to happen in the init block. But you can do a loop that will allocate 100 of these filters, which could be useful for something like a reverb. So it's not really dynamic allocation, but it's more dynamic than using the pseudo objects. We touched on that in a lot of streams ago. We talked about pseudo objects when Gerent was over at Aria's channel. We talked about how you can use pseudo objects. And I think that my implementation has a different trade-off. It's good in some aspects, bad in other aspects. Let me double check this. And Okay, let me take this from the top because this is so detail oriented. Big A plus 1 minus big A minus 1 times cos omega, that is always there, plus 2 times, and that is always there as well. So here, I guess I will do it column oriented just to mix things up. So it is, I think it will be better for my brain. So it's big A, 2 times big A, nothing, minus 2, and nothing. And this is always big A, and it's plus, minus, mistake, plus, minus, plus, minus, it's always big A, it's always 1, minus, plus, minus, plus, minus, it's always omega, and then this one is plus that term. The term seems correct. It's plus that term, nothing at all, minus that term, plus that term, and minus that term. Okay, I think I got it. Let's do the high shelf. And I think I'm going to copy over all the equations because they're going to be similar. So what do we have here? We have, I'm going to do it column-wise again. So big A minus 2 times big A, nothing, 2 times nothing, and then over here, oh, look at that. It is the same now. Oh, these are reversed. And just like that, these are the same. And then these terms are all the same. Just like that, we are done. Okay, I'm going to keep this document around. There are probably some mistakes, but I'm going to catch up with chat. I'm going to commit what I have, and then we are going to continue because I want to hear this. It needs to work. I can send you the code from my queue if you want, but what would be the fun in that? I quadruple checked it. Though I see we're changing some variable names. Yes, I am changing some variable names, and it's okay. I think I got it. I will double check. I will hear things, and I will check this again later off stream. It's kind of boring watching a guy quadruple check all his equations. So we are going to commit what we have, but thanks for offering. That's nice of you. We did a lot, so I'm not even going to bother. I'm just going to commit what we have. Now, this is just the configuration. Now, I need to run this actually. So let's have another function that will also receive the RBJ filter, and I'm going to call this function step. What does a filter do? Next, compute. I'm going to say filter. I think that's what the filter does. So I receive a sample, and then let's get the equation. Oh, I forgot something super important, didn't I? I forgot to normalize. So in the equation that we use here, everything is normalized with respect to A0. So let's normalize with respect to A0 as well. So at the end of the computation, I'm going to normalize. I'm going to grab all of these guys except for A0, and I'm going to format them this way. I'm going to put a cursor, and I'm going to divide all of them by A0. Now that's the right situation to store. Then I guess I'm going to grab this equation. So this is the equation that I want to have. And okay. I would personally use configuration from that variable name. Just using type ? It's one of those commonly mistyped words. But I know you like to be explicit. I don't know which variable you're talking about. If you make a function that does the ramping values thing, that would be helpful. I still haven't figured those out. I think it's on my to-do list, but if it's not, let's put it right now. Let's check the to-do list. Follower, yes, it's there. I'll work on it. I will work on that. So this is the equation that we need to implement over here. How about I have some local variables for this? And I feel like I was thinking about something before, but I lost track of what I was thinking. I don't know. So we are going to need some axes. I think we are only going to need them once. So I may not need special variables for these guys. Yeah, we'll see. So I have a struct, and I'm going to get something. No, I'm going to set something into that struct. No, it will not be that easy. I will need some local variables. At least I will need X and Y. I don't think I need the B's. I don't think I need to get the B's. I think I'll need the X and Y. Okay, so I have a data structure. Oh yeah, so I went into the chat because I wanted to talk to you all about something. And that something had to do with the implementation that Arya was talking about. In his implementation, we actually extracted the RBJ filter into a function. But in that function, you had to be explicit and pass x1, x2, or xn, xn minus 1, xn minus 2, yn minus 2, yn minus 1, yn minus 2, and so forth. You had to pass along all these variables that are used here. I think that you even had to pass along the b's and the a's. And that's sometimes fine, but it's a burden. You, as the user of that function, you have to keep track of all these guys, and you have to update all these a and b's yourself. So there is a lot of knowledge that you need to have in order to be able to use that function. But with this function, I have encapsulated all that knowledge in the data structure. So the use of this function will be a lot simpler. I don't think I'll have time to do that today, but to use this function, we are going to do that on, tomorrow. But to use this function, you just have to set everything up, and then you just call this filter function with a new sample, and you're good to go. This RBJ filter stores all the information you need to run the filter. So that's why I have it like this. Okay, so let me split this, and I will need to get a hold of my A's and B's as well. And it's actually similar to that. So I guess I can just do this. Oh, and it's B and A and X and Y. And then I have to push stuff into X and Y. So let me get X and Y as well. Let me find my RBJ filter. And then we have X and we have Y. Okay. So now we need to push the sample into X. So this X has been initialized to a circular buffer. So my X variable and my Y variable, they are circular buffers, and A and B are arrays. So I can use circular buffer, and what is the name? It is set. It's not really a good name because I'm not setting, I'm like pushing into the buffer, but whatever. What is the buffer? X. What is the value? Sample. And then I am going to set into Y the result of the lovely little formula. So let's get a hold of B0. For that, I need to use an array function. And it's probably called array get. And I need to pass B and the index 0 times X is a circular buffer, so I have to use the circular buffer get X at position 0. So now we are thinking about this n is embedded in the notion of the circular buffer. I just need to know how many samples ago. 0 samples ago, 1 sample ago, 2 samples ago. And I guess I will have -0 here just for good measure. So that is me adding, and then let's subtract from using the A coefficients. We need the coefficient at position 1 and position 2, so that much was correct. And we are doing that with the Y's. I think that's it. I think I implemented the thing. Let's see what you all think. Okay, you all just agree with me. Okay, so I think that concludes the implementation. Now, is it going to work? That's what we are going to find out tomorrow. For now, thank you all for watching this. Thank you for being here. Thank you for being great. Let's see if you have any final comments. You don't. So tomorrow at the same time, we are going to continue this. Thank you all. You're great. Have a great one. Have a good one. Be awesome to each other. I hope you learned something. I hope you can use it. Bye.